Hello students, in my last video, I discussed the stationary eigenstate of harmonic oscillator, and in this class, I am going to discuss about the coherent states. So the coherent states can be constructed using linear superposition of eigenstate of stationary eigenstates of harmonic oscillator. So these coherent states are very useful both theoretically and for applied physics, and and these coherent states are very closely related or closely resembles the classical behavior of harmonic oscillator. So mathematically, uh, a coherent state denoted by alpha is defined as the eigenstate of annihilation operator. So alpha is your coherent state, and now I want to write this coherent state as a linear superposition of uh, eigenstates of harmonic oscillator. So what are the key properties of these states? So these states have a exhibit minimum uncertainty limit, that is they are Gaussian and not spreading over time. And if I calculate the mean position and mean momentum, they oscillate exactly like your classical simple harmonic oscillator. So let us now write the state as a superposition of eigenstate of harmonic oscillator, where Cn is your n alpha. Now this coefficient we need to calculate in order to write alpha as a superposition. So let us calculate this. So for that I use a definition of coherent state, which is the eigenstate of annihilation operator. Now, if I operate bra n from the left side, this gives me alpha n alpha values. I need to calculate n alpha. So now let us operate a dagger on n. When I operate n dagger on n, this gives me n plus 1, and state raises by 1 unit, n plus 1. And now if I take the adjoint of this one or complex conjugate of this equation, so this a dagger is becomes a, and this cat become bra. Similarly here this cat also become bra. So this become na. Now if I operate alpha from alpha cat from the right side, so this equation turns out to be like this, and now I can write n a alpha like alpha and alpha from the above expression. So now this equation becomes n plus 1, and the cat n plus 1 alpha is equal to alpha and alpha. Now let us reduce this replace this n by n minus 1. So if I replace this n by n minus 1, so what will become? So this equation become n alpha, and this become n, and this become n minus 1 alpha. So similarly, now if I keep on decreasing this n minus 1, if I write this n minus 2, this will remain like the same. If I change now this one n minus 1 alpha, like I change here, if I make it replace it by n minus 2, then what will become? 1 alpha will come more, and under root n minus 1 will come, n minus 1 will come. Similarly, yeah, I can keep on converting this, replacing here n minus 2 to n minus 3. So alpha q and n minus 1 n minus 2 will come. Like that I keep on going up to n terms. This become alpha n, and this is under root factorial, this become factorial n, and this is 0 alpha. So now this is my value I need to calculate, and if I will use this value in my definition of coherent state superposition of eigenstate, this expression comes out like this. Now we need to normalize the state. So when I normalize this state, I can find the value of uh, this coefficient as e power minus alpha square, because when I multiply it by bra alpha, what will happen? This become mod alpha square, and this will become mod of alpha square, yeah, alpha star n, and mod of alpha square power 2n, and this become factorial n. Root will disappear, and n will become 1. So So the value of this coefficient, which comes out e power minus alpha square 2 after taking root. And now this is my final expression of coherent state as a superposition of eigenstates of harmonic oscillator. Again, this n can be written as a dagger n upon factorial n, root factorial n. So this is my final expression for the coherent state as a superposition of um, eigenstate of harmonic oscillator. Sometimes this expression is asked in the exams. And now Coherent state has a many application, as I told, theoretical and technological applications. Some of these applications are they are used in quantum optics and laser, where laser state is defined by the coherent state is a coherent state, and similarly they are used in gravitational wave detectors because of their minimized quantum fluctuations. They can be used in quantum information and communication, and they are useful for explaining quantum entanglement, teleportation, and squeezing. Similarly, uh, they are used as a semi-classical approximation of quantum system where quantum and classical behavior coexist. They are used in path integrals, quantum field theory. So, and they can be also used in quantum simulation and state reconstruction. They simplify simulation of oscillator system and are used in state tomography via phase space distribution like Hazmi Q functions. So this is the description of quantum coherent states. So in my next video, I will come some more detail about these states. We'll calculate the expectation. We'll see the orthogonality and completeness relation of these coherent states, and we will also calculate expectation value of values of x for these quantum state. I'll stop here. Thank you very much.